Hi guys, my name is Robinson George Adishil and this is my project demonstration for my custom operating system project. I'm attempting to build a bare metal OS for the ESP32 microcontroller that I'm calling Null32. In my previous milestone, I successfully booted a binary blob from an SD card, but that isn't really how a true operating system should behave. It was basically just a function where it allocated some space, jumped to that area, and allowed for execution. To be a real OS, or at least to provide to be a seed for an operating system, the kernel needs to run directly from the beginning of the IRAM, right from the start of the boot sequence. To handle this, I've implemented a trampoline function which I ran in extensile assembly. This allows me to copy the operating system from the DRAM using the bootstrap loader into the into the DRAM itself, and then the trampoline function into the upper IRAM. The code then proceeds to go to the trampoline function, which is in the upper IRAM. The trampoline function then copies the operating system from the DRAM into the IRAM and jumps to that to will actually start executing, which allows it to function as a true standalone operating system. In addition to the loader, I've built a hardware abstraction layer with support for GPIO, UART, SPI, and SD card reading support using the FAT32 file system. This is a major support because it lets the OS actually understand the file structure on the disk instead of just reading raw binary sectors. We have full support for file operations including read, write, delete, list directory. Looking at the file explorer on my computer, you can actually see multiple programs alongside our main kernel binary, including another file called example.txt. In example.txt, we can actually see the content of before writing. Now, we can actually use this for a live demonstration. Now let's eject the SD card and put it into the ESP32. After hitting the reset button, the system initializes. You can see the SPI and the SD cards or protocols are working perfectly in the terminal, and everything is working great. Now let's actually do something. Let's actually list all the directories on our SD card, so we can actually see everything here, including the file name and its size. Now let's actually modify that file that we created. Let's actually first let's read from that file. So let's read example.txt and let's see what it has before writing. Let's modify that file. Let's write to that file. Let's write example.txt and let's just write after writing in all caps. Let's verify that it's actually been written to, and let's just go and see what happens. And as you can see, it says write successful, which means it has been successfully able to write. Now there is a bug in my system where I can only write in capitals and only writes as a capital, but on Windows it automatically converts it to lowercase, and I will have to debug that. But you can see that it actually does work. We can actually see an output saying after writing, which actually confirms that it's writing. Now let's just actually look at the next. Let's look at file deletion. Let's see if we can delete the file that we have just created. So by inserting the SD card back into the ESP and we resetting it, let's delete that file, example.txt. Now we don't actually know if the delete command actually works. We just know that it's been sent. Let's verify that it's actually been deleted by looking at it from our Windows file system. Now when the SD card deleting it's never a truly deleting. It just deletes the entry in the master boot record. It never existed. It says the entries or the sectors are free. It's available to be written, so the OS can override it later. And the second example.txt is gone. Now, back on the computer, the file is gone. Now the file system is stable. Now we can go on to the best part, running an external program to truly prove that I've developed a batch operating system. This is all bare metal C. I'm not using any standard libraries except for stdint for the fixed width integers like 8-bit, 16-bit, and 32 bits. There's no printf, there's no malloc. It's all manual register manipulation. That is why this UART interface is so critical. Now, let's run a program called scanner.txt. After inserting the SD card back in, and by clearing this, let's reset the ESP. Now let's run a program. Let's run a program called scanner.txt. Once I type this, the onboard LEDs begin a scanning pattern immediately. I've also implemented a break command which allows us to stop the program. Unfortunately, we can't control where it stops. It depends on how fast it reads it. But it stops at like a, well, relatively random instruction, but we'll need to refine it later. Now let's run another program called powerup.txt. In this one, the LEDs pretend to be charging up and then discharge immediately, kind of like in like a video game or something. Now let's actually modify the delays on. Let's actually modify the delays that are present inside this program. Now I've just reset this so I can stop the LEDs from flashing. If we wait for it, okay, it opened up. We go to power.txt. Let's change from 150 milliseconds to 300 milliseconds. Now this is the delay, and this is the pin of which the GPIO pin of which is affected. So we're going to go here, click this, and modify everything until everything says 300 milliseconds. So now let's save it, close it, eject it. We're going to put it back into the SD card. We're going to clear this thing and we're going to restart it. Now let's just run the program, which is 0, powerup.txt, and it's significantly slower now. This proves that the kernel is actually actively reading and executing those values straight from the hardware. That wraps up my Milestone 2 for Null32 OS. We have a working trampoline loader, a solid hardware abstraction layer, and a functional file system, even with that bug. Anyways, thanks for watching, and let me know if you have any suggestions. Bye!